Welcome to my lecture series Random Variables and Stochastic Process. In this video we are going to discuss about the total probability theorem as well as the Bayes theorem. The first one we go for the total probability theorem. Let's consider we are having a number of mutually exclusive events, and all those mutually exclusive events are having some common features. Now to extract those common features we are going to be using the total probability theorem. Come to the statement here. Let b1 comma b2 comma b3 and so on bn are n mutually exclusive events, means bi intersection bj is equal to pi, where I is not equal to the j. Under this condition, and all these events have a common feature or element as a, then the probability of a is calculated using total probability as P of A equal to summation of I equal to 1 to n probability of A given Bi into probability of Bi. This what actually the corresponding statement is. Now we go for the corresponding proof here. Let's consider we are having a sample space S, and all this particular sample space is having n number of mutually exclusive events such like this. Such as b1, b2, b3, b4, b5 and so on, bn number of mutually exclusive events, and all these events are having a common feature represented as A over here. Then we are going to be finding the probability of this particular common feature, and that what actually comes under the total probability theorem. Come to the proof over here. Consider we know b1 union b2 union b3 and so on bn gives a sample space S. We come to know that A is the subset of S. Then we can write A is equal to A intersection S or S intersection A. Now submitting the corresponding S equation number 1 in the equation number 2, we get A equal to union of I equal to 1 to n, where A equal to I equal to 1 to n Bi intersection A. This is further carried over here as A equal to union of I equal to 1 to n A intersection Bi. Now apply probability on both sides. Then probability of A equal to probability of union of I equal to 1 to n A intersection Bi, and as per the axiom probability, axiom theory, axiomatic definitions, we are going to write this as this union is going to be become sum of I equal to 1 to n. Then take the probability into the terms. Probability of A intersection Bi is nothing but the P of A. On applying the conditional probability, then we know probability of A given Bi equal to probability of A intersection Bi into probability of Bi, sorry, by probability of Bi. Then we can write the probability of A intersection Bi equal to probability of A given Bi into probability of Bi. Submitting the same in the equation number 3, submitting this 4, equation number 4 in the equation number 3, then we get P of A equal to summation of I equal to 1 to n probability of A given Bi into probability of Ba. This is what actually the corresponding total probability theorem is. Whereas in the Bayes theorem, come to the statement here, that we are having B1 comma B2 comma B3 and so on Bn are mutually exclusive events, means Bi intersection Bj is not equal to, sorry, is equal to pi where Bi, where I is not equal to the j. Then all these have a feature A. Then now let's consider the probability of, means we are going to be having the corresponding A component, and that is get collected from the respective I is to be calculated by using this Bayes theorem as probability of A given Bi into probability of Bi by probability of A. This is what actually we need to prove. In order to prove this one, this is what actually we need to prove. Come to the proof. In order to prove this one, we know that B1, B2, B3 all are mutually exclusive events. Now we are going to take a conditional probability. Yes, probability of A given Bi equal to probability of A intersection Bi by probability of Ba. This further we can write it as probability of A intersection Bi equal to probability of A given Bi into probability of Bi. Let's consider this the equation number 1. Next we go for probability of Bi given A. And this can further written as probability of A intersection Bi by probability of A. And over here, let's consider this the equation number 2. Substitute 1 into, we get probability of Bi given A equal to probability of A given Bi into probability of Bi by probability of A. This is what actually the corresponding Bayes theorem is. Here the Bayes theorem is mainly used to calculate the probability of getting a one particular common feature with respect to, here the Bayes theorem is mainly used to calculate the probability of getting a feature from a particular component. Let's consider if any patient having fever, and we are going to be using this particular mechanism in order to find, and the patient get the fever due to a particular reason. The probability of the particular reason is going to be get calculated over here. So with this we are going to be close our session over here. In the next session we are going to discuss about the different problems on the total probability as well as the conjunctive